Hi everyone, I'm Toby. I'm a software engineer at Google, and I would like to talk to you a little bit about our measurement work regarding traffic policing on the web. And this is joint work with other folks at Google and also at USC. So just to kick things off, let me put everything into a little bit of context. When we talk about internet measurements, we usually have three involved parties. We have content providers that provide you services like shopping, search, or video streaming. On the other hand, we have the users that consume these services and pay for them. And in the middle, gluing everything together are the internet service providers. Now, in recent years, this kind of environment has undergone some drastic changes. So for one thing, what happened is that we've seen an exponential growth of video traffic. The two video providers named here, YouTube and Netflix alone, account for roughly 50% of the traffic in North America. What all of these content providers have in common, though, is that they want to maximize the quality of experience for their users. So what this often means is we need a high bitrate with low tolerance for latency and packet loss. Now, orthogonal to that, the ISPs have slightly different goals. They want to accommodate a multitude of services and policies, and they often use this by using some form of traffic engineering. So one form of traffic engineering can have the goal of just enforcing a rate limit or maximum throughput. And there are two common ways to do this. The first one is you just drop packets once you reach a throughput limit. This is known as traffic policing. The alternative option is to use a queue, and then you queue packets and send them out at the maximum rate that you want to enforce. And this is called traffic shaping. Now, I want to make it clear that in this talk, I'm only focusing on traffic policing, and traffic shaping is only tangentially involved here. All right, so the contribution of our work is that we want to analyze the prevalence and impact of traffic policing around the world, and then also look a little bit of what can we do about policers and mitigate their potential negative side effects. So this is roughly how the talk is going to be structured. I'm going to tell you a little bit about how policing works, then how we detect it in packet captures, and then provide some measurement results, and finally talk about how we can mitigate their impact. So let's get started. I'm just going to give you a very simple example how a policer works for those of you who don't know about it. So you have an input link, an output link. In the middle, you have a policer, and the policer has some state in the form of a token bucket. Now, what the policer is doing is it's refreshing tokens at the predefined policing rate you want to enforce. Now, when a packet is coming in, the policer is simply checking if there's a token available. And if that's the case, it's consuming a token and sending the packet out. If there's no token available when a packet is coming in, then it just drops the packet immediately. Now let me show you what this can do in practice. Throughout the talk, I'm going to show you a couple of these sequence diagrams where you have time on the x-axis, sequence number, or progress on the y-axis. So the first thing I'm showing you here is the throughput that this policer wants to allow over time, this yellow dashed line. Now what a lot of token buckets policers also do is they allow some kind of burstiness. So if your connection isn't immediately sending traffic, you can have an initial burst from these saved tokens. So this policing limit is shifted upwards. So now I'm going to show you a connection that we actually observed in practice and how it interacted with a policer. I'm going to show you the real data as the blue circles and then the retransmissions or losses as red ones. So what you see in the beginning is that this connection is doing what TCP classically does in the beginning, is it's overshooting. You have slow start with exponential growth of your transmission rates. And because you had this initial burst where the police is essentially letting data through at unlimited rate, you're overshooting in this case by about 1 megabyte. What's happening afterwards is that you have multiple rounds of retransmissions where TCP is trying to figure out what's going on, and this is recovering from this packet loss. Now this particular trace is a YouTube trace, so what is happening afterwards is you have this kind of idle period where you're not transmitting a video chunk anymore. And then after you start transmitting the next video chunk, you have again slightly slight number of buffered tokens, so you can recover fairly quickly from the wasted throughput earlier. And in the end, you roughly match the transmission rate to the policing rate. Now, policing can have negative side effects for all the three parties that I mentioned initially. It can be bad for the content providers because you're producing an excess load on the servers that are forced to retransmit dropped packets. Just as a spoiler for results I'm presenting later, the global average, you see 20% retransmissions when policing is involved versus 2% when no policing is involved. For the ISPs, it can also have some negative impact because it is transporting traffic across the internet only for it to be dropped by a policer very closely located to the user. And finally, for the users, it can have bad impact because it's interacting badly with TCP-based connections. And I'm going to show you that we actually measured degraded video quality of experience, which then can lead to user dissatisfaction. All right, so let me tell you how we actually analyze the prevalence and impact of policing at scale. We first develop a mechanism to detect policing from packet captures from the server side. We then tie this information back to application metrics that are already collected on the client side. And global scale we achieve by collecting packet traces from almost every Google front end across the world. So the analysis pipeline looks roughly like this. So we want to serve an HTTP response, like a video chunk to a client. The client's already collecting application metrics. And what we do is we collect sampled packet traces on the server side, do some post-processing at the backend where we detect policing, and then cross-reference this with the application metrics. So let me quickly show you how we detect policing from server-side traces only. So again, we have a policer that wants to enforce a policing rate. Now the key info here is that we know that whenever you stay below that rate line, packets should pass through the policer. Whenever you go above that policing line, the packets should be dropped by the policer. And in fact, the packets will always be dropped when we cross this diagonal policing rate line. So we will use that knowledge to detect policing and packet captures. So here's a sample capture to simplify how we're actually doing this. So you can see you're making progress over time with occasional packet losses. So the first thing we want to do is we want to find what's the policing rate. And here, again, from the knowledge I showed you in the previous slide, we used the measured throughput between an early loss as an estimate, simply because we think that the losses are caused by a policer. In the next step, we then match the performance to the expected policing behavior. So again, everything above that diagonal policing rate line should get dropped. Everything below, or almost everything below, should go through. Now I'm saying here almost because there can be other causes for packet drops, so we allow for a little bit of noise for losses that happen when you stay below that diagonal line. Okay, so it's important for us that we avoid falsely labeling loss as policing. So I'm showing you a couple of examples that hopefully convince you that we can achieve this. So in this particular example, you see that the throughput is ramping up over time with occasional packet loss. So again, our algorithm would draw this imaginary policing rate line. And you can see here that the losses that happen in this case, they all happen when you stay below the line. So this isn't consistent with what we would expect from a policer. A policer would not have dropped these packets. Now similarly, here's another example which looks a little bit more involved. Again, we draw the policing rate line, and in this case you can see that there's actually a phase where we go well beyond the policing rate line. So a policer would have dropped traffic immediately when you cross that line. So again, this is not consistent with what we expect from a policer. Now, one common criticism we heard is, well, policing can actually look very similar to congestion. How do we distinguish between these two? So the key knowledge we use here is that packets are usually dropped when a router's buffer is already full. And we also know that when a buffer fills up, we do experience queuing delay. So what we do is we use inflated latency as an additional signal that can indicate that there's actually no policing involved. So in this particular case, I'm showing you here as on a separate axis how latency measurements could look like. So and if we see that the latency is actually spiking at the same time where we see packet loss, we use this as evidence that it might not be policing and rather rule it out. All right, so the paper that is accompanying this talk has a lot of information about validation, so I'm not going to go into detail about this, But suffice it to say, we have two kind of validation setups. The first one is a lab setting where we just create our own traffic with policing involved, shaping involved, congestion. And then with this ground truth, we try to figure out how often is our algorithm actually correct. And while we don't detect policing in all the cases, it was very important to us that we actually don't produce false positives. So the results I'm going to show you later likely underestimate the amount of policing that is present in the web. A second validation step was where was based on us looking into some deep dives. So here I'm showing you for 5 ISPs how the policing rate distribution looked like that we saw. What you can see is that for each of these ISPs, we only observed few policing rates. And in fact, for 4 out of these 5 ISPs, we could confirm that these rates match the data plan. For the 5th ISPs, we couldn't do that because it was defunct at the time that we did this analysis. We also confirmed that for all the other ISPs, that their policing rates cluster around a few values across the whole data set. And finally, we observed no such consistency across the flows where we didn't detect policing. So this gives us a little bit more confidence that we're doing the right thing here. All right, so in the second part of the talk, I want to talk a little bit about our measurements results and then finally talk about what we can do about all this. So we did an internet-wide measurement campaign in late 2015. We sampled data for 7 days from almost all Google front ends. That gave us about 270 billion TCP packets. And to tie TCP performance back to application performance, we actually analyzed everything in HTTP request response granularity. So we wanted to figure out how bad did a video chunk, for example, perform when policing was involved for that particular chunk. Okay, so let me start with a couple of results. The first thing is actually quite promising, which is talking about the prevalence policing across the web. So here I'm showing you how many of the segments that we captured actually had policing, and the numbers are really low. This is great. But then we actually want to look at, well, what about the connections that actually perform poorly? And what we see in these lossy connections is that up to 7% of them have policing involved. The next thing we looked at was what kind of differences did we see between these policed and non-policed connections. The first metric we looked at was packet loss. So here I'm showing you the average packet loss for policed and non-policed connections across the world. And what you can see is that on the average, we see about 2% loss when no policing is involved, and about 20% loss or more when policing is involved. Now, 20% loss is a huge number because TCP usually breaks down at these kind of packet loss rates and has a tough time recovering from it. Now, we were interested in where do these huge packet loss numbers actually come from? And the answer lies in this graph I showed you earlier. So we can simplify this graph a little bit. We can actually look at the throughput curves in 2 different phases of this connection. The first one is the burst throughput happening before the police actually kicks in. And the second one is the policer enforcing the policing rate. Now what you can see is that there is this inflection point where we suddenly have a very sudden change in bandwidth. And TCP really doesn't like sudden changes in bandwidth. Now when we looked at the burst throughput versus the policing rate that we see, you can see that on average we have policing rates that are over 50% lower than the burst throughput rate. And this is, by the way, a log scale on the x-axis. In the 90th percentile, the policing rate is 10 times lower than the burst you can initially produce when going through a policer. And that's why these loss rates are so large, because TCP cannot recover from them quickly enough. All right, so the most important thing we looked at was the quality of experience. And here we look at 2 things. The first one is the rebuffering time. So this is the time that a video is paused after a playback started due to insufficient stream data being buffered. And we contrast that to the watch time. So that's the fraction of the video watched by the user. Now the ratio between these two should optimally be 0, which means that as soon as you start playing a video, you should never rebuffer and show that spinning wheel of death. Now what we see in practice is that policing can have an effect on this metric. So here I'm showing you one graph where we looked at the playbacks with similar throughput and then just single out the policed playbacks. What you can see is in the tail, the police segments can have to up to 200% higher rebuffering times. All right, so much about our measurement results. I would like to spend the rest of the talk talking a little bit about how we can mitigate policer impact. And we separate this in two categories. What can content providers do, and what can the policing ISPs do? Now there are different constraints involved here. The content providers have no access to the police, and typically they don't know what kind of configurations were used. But what they can do is they can control the transmission patterns to minimize the chance of hitting a token bucket when it's empty. The policing ISPs, they have access to these policers and their configurations, so they can deploy alternative traffic management techniques if they wanted to. So in the paper we wrote, we looked at 5 different things, and I invite you to take a look at the paper for more details. We looked at rate limiting, pacing, and some ways to reduce packet losses during TCP's recovery to improve performance. On the policing ISP side, we looked at can we maybe tune these policers to use better configurations, or shaping as an alternative traffic engineering technique. Now I want to spend time a little bit on 2 additional efforts that came up after we originally published the paper, which is we can model police explicitly on the content provider side, and then shared across both realms, we can actually incorporate data plan information to make better decisions. So let's start with how we can model policers. So for a little bit context, the way this came up for us at Google was as part of a new congestion control mechanism called BBR. This was published late last year in ACMQ. BBR stands for bottleneck bandwidth and round trip propagation time. And the key goal here is that we seek high throughput with small queues by programming bandwidth and RTT sequentially. So this goes away a little bit from what TCP congestion control typically does, which is send as fast and as much as you can until you hit packet loss, and then you slow down. So we have an explicit model of a bottleneck in the BBR. So we're tracking the maximum bandwidth and the minimum RTT, using some windowed max-min filters to figure out what is the optimal bandwidth, and then we pace near that bandwidth. And then on loss, we reduce the current delivery rate, but reprobe very quickly. So this is very different from what typical congestion control does. So BBR is modeling policers explicitly, since we figured out that policer can have bad impact on our connections. So what we do is similar to what our detection algorithm for our measurement campaign did. We have a long-term sampling interval, typically between 4 and 16 round trips. And we start and end again with packet loss based on the assumption that we want to measure what's happening when the token buckets are actually empty. And we record the average throughput and the packet loss rates over each of these intervals. Now, if 2 consecutive intervals have very high loss and roughly the same kind of throughput, then we estimate that policing is involved, and we just transmit at the average of these rates for quite a while. Now, there are a ton of magic numbers in this slide here, right? So these might need to be tuned for different content providers differently. And we figured out these values based on measurement sweeps, and they work pretty well for our purposes. So let's see how this would work based on that trace I showed you earlier. So again, we would have this initial burst. BBR wouldn't necessarily work differently there. But what we do is we have these 2 sampling intervals when we have these when we have the loss recovery involved, and we would see that the throughput is essentially the same during these recovery periods. So at that point, BBR would just continue transmitting at this rate, and thereby reducing the risk that we hit an empty token bucket again. Now here I'm showing you another trace, which is a little bit longer. This is a police YouTube trace. So again, you see at the beginning these collection of red dots where we initially detect the policer, and then we're performing pretty well over time without mostly any loss. You can see in about 10-second intervals that there is policing involved again, so we see again packet loss. And this is caused by the congestion control deciding that it actually wants to reprobe every once in a while to figure out if there's maybe more bandwidth available. So we don't want to be stuck at this average policing rate for forever. All right, so there's one last thing I want to talk about, which is what can content providers and these ISPs maybe do together. And there's one effort that some colleagues developed a little while ago, which is a mobile data plan API. The problem with policing is often that the content providers are unaware of their configurations. With the mobile data plan API, the applications can actually request information about a user's data plan from the mobile network operator, and then the content provider can incorporate that kind of information to improve the quality of experience. So for example, YouTube can actually customize the video quality or its transmission rate if we actually know beforehand what the policing rate is like. So we reduce the amount of packet loss by just transmitting at a rate which is slightly lower than what a policer likes. If you like more, there's an email address there so you can contact. All right, so just to wrap up and leave some time for questions. ISPs need ways to deal with increasing traffic demands, and they want to enforce plans. So traffic policing is one option to actually do this. On a global scale, we see up to 7% of lossy segments being affected by traffic policing. And I showed you that police connections can see much higher loss rates. They can see long recovery times when policers allow initial bursts. And we can see worse video rebuffering times or quality of experience. Now, the negative effects that can be caused by police can be mitigated. I showed you some solutions for the content providers as well as for the ISPs. If you have questions, feel free to email us at the address there. There's also an adjunct data and tech report publicly available at GitHub. This I developed as part of my PhD work at USC, and feel free to check out the slides. And with that, I thank you for your attention.
Any questions, comments?
Hi, Jay Gillenfiner. Have you had any positive response from ISPs for this notion of the mobile data plan API?
I can't answer that since I'm not involved in the mobile data plan API. I would have to check back on that with other developers.
Okay, and follow-on question was, have you given any thought to potential unintended consequences of something like BBR, playing around with retransmission and all the factors that you have, and as you yourself said, you had to come up with some magic numbers which may not apply across all networks. Any thoughts about how to avoid some kind of a storm caused by this?
So I can tell you that the BBR team played around with this for multiple years before they actually said, okay, these are the numbers we want to look at. I totally agree that these numbers probably won't work for every single situation. I think the decision was there, we use the numbers that work for the huge majority of people and improve their performance at the slight cost that maybe for a tail of customers, they might make things a little bit worse.
Thank you.
Yeah.
Matt Petak, Yahoo. So to clarify on that, your lab examples look very clean in terms of here's the police or here's our traffic flows. Real world, you've got a lot of different competing traffic flows. Did you find that you had problems with actually characterizing policers when you have many, many parallel data flows all impinging on the bucket at the same time?
So, so this works for our traffic pattern, and the only reason for that is that we are not trying to transmit multiple chunks in parallel, right? So we kind of have this special setup where we would have a fairly clean signal. Now, what we would like to do more general is, well, it doesn't really matter if we are looking at a single connection here. Police likely doesn't care about that. It cares more about how much traffic is going to this particular user, so we could just throw everything into a single bucket there. The reason we couldn't do that is for privacy purposes. We had no information about customers whatsoever, so we couldn't even say how many customers were affected by policers, right? I think other content providers could potentially do that, and then they should just adjust their mechanism and say, we'll just look at all the traffic going to a user. And that's also one of the reasons why we likely underestimate how much policing is going on. If there's any kind of noise in there, a little bit of noise we can handle. If you have something going on beside watching YouTube, then we probably have a tough time figuring that out.
Gotcha. Thank you.
Phil Rosenthal from IS Prime. I'm wondering, do you have your congestion control algorithm? Is it like available as a pluggable module that others can use and play around with?
BBR has been upstreamed to the Linux kernel a while ago, and as far as I know, there are efforts underway to make this part of FreeBSD as well. Not by Google, though, by other folks.
And so following up on what Matt Petak was asking, I mean, when you have in the real world competing flows, doesn't it just end up that it does end up reaching an equilibrium better than previous algorithms, or it still doesn't help?
Well, so the thing is, I mean, in the worst case, we don't detect the police arm, right? So that's always a risk, in which case BBR will still perform better simply because it isn't so, it doesn't react so aggressively when packet loss is involved. We just can't fine-tune the algorithm in that case. So we will hit the token bucket over and over again if we cannot figure out that there's actually policing involved there. So that's a risk.
Okay. Thank you.
Yep.
Jeff Houston, APNIC. This is sort of another one in a long run of TCP flow control adaptation algorithms. And if I understand what you're saying, you're trying to optimize the flow control where you get packet loss without a corresponding increase in the queuing delay, which is normally what you get with congestion. So you're trying to react to almost random packet drop without advanced signaling under circumstances that you think is policing.
If you have, if you look at the actual numbers, there needs to be 20% packet loss involved here to even trigger this kind of mechanism.
So let me get to where I was going. Most of TCP is basically a round-trip flow control algorithm where you punt in stuff, you wait for one round trip, it tells you how it's going. The whole idea behind flow start and AIMD was to sort of oscillate around what you thought was the sweet spot.
Yes.
You've removed that in this algorithm. So the first point is, do you ramp up as efficiently as AIMD, or do you take slower in BBR to get to what you think is the optimal rate? And secondly, do you adapt aggressively to competing flows, or does it take you some time to sense that someone else is flogging bandwidth and you need to adjust? So are you less sensitive, as Sally Floyd used to say, in this kind of algorithm?
I can't answer this exactly because I haven't worked on the BBR algorithm. I really invite you to look at the BBR paper. There has been, Google has done extensive evaluation, and even on the BBR-dev mailing list, there has been extensive evaluation by other parties that looked at, can this actually work in the internet? I think the main consensus is yes, it works better, but I am certain there have been lots of studies where they figured out, well, in this particular setting, it actually sucks a lot. And then people have to look at it again and see, can we actually deal with this, or is this just a corner case?
Thank you.
All right. All right, thanks.